Hello there, this is Truth Socrates. Welcome to our video for today, which will be about the calculus of inverse trigonometric functions. So let me show you what we are going to do today. Our goals are to construct the inverse sine, the inverse cosine, and the inverse tangent functions. We're going to make them from scratch. We will show how to restrict the parent functions in order to construct these inverse functions. We will do some calculus. We will find the derivatives of these functions. And anytime we have a derivative formula, we have a corresponding antiderivative formula. And once we have these, we will do some examples where we will find some derivatives and some antiderivatives. Okay, but before we can invert any function, we first need to check whether it is what's called an injective function or a one-to-one function. So, how do we know when a function is injective? It happens when the only solution to the equation f of a1 equals f of a2 is the obvious case when a1 equals a2. So in other words, if you input two different numbers, a1 and a2, then the outputs, f of a1 and f of a2, also have to be different. So this means that if you plot the points corresponding to a1 and a2, they should not have the same y-coordinate. All right, so because of this condition, we have a graphical way to check, in other words, with our own eyes, when a function is injective. It's called the horizontal line test, and it basically means that every horizontal line must intersect the graph of the function at most once. In other words, you can't intersect it twice or more times. So this is a problem for our trig functions because all of them are periodic, right? They repeat every 2 pi, and even worse than that, within any period, they also repeat themselves, well, except for the tangent function, I guess. Okay, so what we're going to do in a few minutes is we will restrict these functions on a smaller domain, a smaller interval, so that once we restrict them, then they become injective or one-to-one on that interval. All right, so once we know that our function is injective, then we can get serious about finding its inverse. Okay, so our next condition is that we have a function from some set A to some set B, and then we already know that the function is injective or one-to-one. Okay, we will also require that this set B is already the range of the function. In other words, all the values which are hit by f for some value from the domain. So we also call such a function a surjection or a surjective function in B. Okay, so in other words, every element of B is a target of some element of A. When we have a function which is both injective and surjective, we say that f is bijective. Okay, so all of these words end with active, I guess. We also say that f is a bijection from A to B. Another way to say this is that f creates a one-to-one correspondence between the members of A and the members of B. Okay? Once we know that f is bijective, then we can construct its inverse function. So we will use the letter g, and this time it will be a function from B back to A. Right? So how are we going to construct this function? We have to define g of B for any member little b of capital B. Okay? We already assured ourselves that B is the range of f. So there is at least one element little a from the domain capital A where f of A is B. Okay? But by the injective property, there is exactly one such element. Okay? So let's scroll up a little bit. There's exactly one element from the domain with this property. So now we can define g of B as this element A. We also call g of x the inverse of f of x, and we can write it in this notation, and it is pronounced g of x is f inverse of x. So let me warn you, it does not mean reciprocal. It means the inverse of x. if you're not comfortable with that, think of g as the reverse function. Okay, so when you think of reverse, there's no multiplication involved, no division involved. You're reversing what f does from a to b. All right, now based on this construction, we get what are called cancellation laws or properties involving these two functions, f and its inverse g. For every member little a from capital A, the domain, g of f of a is the same as g of b. We said that f of a is b, but we also said that g of b is a, right? So put all together, g of f of a is the same as a. And similarly, if little b is from the range capital B, then f of g of b, we said that g of b is a, that makes f of a, which we said is equal to b, right? So in other words, f of g of b is the same as b, okay? Now, both of these left sides can be written as the composition of two functions, okay? So the first equation can be rewritten as g composed with f evaluated at a gives you back a. And similarly, f composed with g evaluated at b gives you back b. So in other words, under the process of function composition, these two functions, f and g, cancel each other out. You're back where you started, basically. All right, so with those preliminary definitions, we can now go ahead and actually construct the inverse sine, also known as the arcsine function. What we're going to do next is we're going to hop on to GeoGebra, and you can find it at geogebra.org, my mistake. It's not geogebra.com, but .org. There are several versions. I like to use the classic version. And you might also be wondering, why do I like GeoGebra instead of Desmos? There's nothing wrong with Desmos, but I use GeoGebra in my multivariable calculus as well. And Desmos does not do three-dimensional graphs. So I stick to GeoGebra. I'll see you there in a second. All right, here we go. This is the opening screen of GeoGebra. So we are going to start by graphing the sine function. Okay, so sin. As you can see, there are several options there. So we will use sine of x. There it is. Okay, so that everyone knows what the graph of sine of x looks like. And as we said earlier, it's periodic. It repeats itself every period of 2 pi. So you can see it there. And it's definitely not 1-to-1. Okay, so if you graph a horizontal line like y equals 1/2, whoops, you are hitting more than 1 point. Okay, so of course we're hitting an infinite number of points. Okay, so we mentioned that if this happens, we can try to restrict the domain of the function so that it's 1-to-1 on that smaller domain. Okay, so if we don't want to go far from the origin, then it looks like we need to erase all the parts of the function to the right of this maximum point, and I hope everyone knows that that happens at pi over 2. Okay, so similarly, if we don't want to hit more than 2 points, well, more than 1 point with this horizontal line at -1/2, then it looks like we have to erase all the parts of the graph to the left of this minimum, which is -pi over 2. Okay. So to do that, we can specify the domain of our function by including an interval. So we'll put comma, and we'll say -pi over 2 is less than or equal to x, and less than or equal to +pi over 2. And there it is. So our f, our sine of x, is now restricted between -pi over 2 and +pi over 2. Okay, so any horizontal line will intersect that graph at most once. Okay, obviously if you go beyond 1, you're not going to intersect the graph at all. Okay, and there's nothing wrong with that. So with that, we can now graph the inverse function. Okay, so we are going to construct a function now where the domain of the inverse function is -1 to 1, and the range is from -π/2 to +π/2. Okay, so GeoGebra can do that for us. There it is. There is arc sine. Okay, so arc sin of x. There it is. Okay, so the roles of x and y are now exchanged. Okay, so if sine of a equals b, then inverse sine of b is equal to a, right? And as you can see here, if you tilt your head 45 degrees like that, these two graphs are symmetric. So the axis of symmetry is y equals x. There you go. See? If you look this way and think of this line as like a mirror, then the blue graph reflects with the red graph. Okay, they are mirror opposites of each other. Okay, so let's summarize what we did in GeoGebra. We saw that the sine function is periodic, so there's no way that it can be injective. Its domain is all real numbers, and its range is from -1 to 1. Okay, so we saw that if we restrict the sine function to between -π/2 and π/2, then that function now passes the horizontal line test, and the range is still 1 to 1. Okay, so in other words, the range is as big as possible. So with that, we are able to construct the inverse sine function. And we said that y equals inverse sine of x means that x is the sine of y, right? So in these two equations, x must be between -1 and +1, and y must be between -π/2 and +π/2. Okay, so I want to give you a little warning on the notation. I used arc sine in GeoGebra, but most of the time, just to save us some writing, we use sine inverse. It looks like a reciprocal, but obviously it is not. It does not mean the reciprocal of sine of x. If we meant the reciprocal of sine of x, we would have written cosecant x from trigonometry. Okay, so this symbol is our shortcut for the arc sine function. Later on, when we talked about the arc cosine and the arc tangent function, same thing. Do not confuse them with 1/cosine or 1/tangent. If we meant a reciprocal, we will write it as secant or cotangent or whatnot. Okay, so let's do some trigonometry. I hope you remember the basic values for some common angles, π/6, π/4, π/3, and we can throw them around the circle. We can look at 2π/3, 5π/6, 7π/4. We can also look at negative angles, -π/6, -5π/6, whatnot. Positive angles go counterclockwise, and negative angles go clockwise. Okay, so let's compute these three numbers. Maybe some of you already figured them out while I was blabbing my head off. So if we want arc sine of 1/2, we are looking for an angle y between -π/2 and π/2, where the sine of that angle is 1/2. Okay, so yeah, -π/2 to π/2, that's the right half of the unit circle. Okay, since we want positive 1/2, we want to be in the first quadrant. And what angle in the first quadrant has sine 1/2? Is it π/6, π/4, π/3? I hope you remember that it is π/6. Okay. Now, how about inverse sine -1/√2? Okay, so hopefully this jogs your memory. We should be thinking of the reference angle π/4. Okay. But since we want -1/2, we should be in the fourth quadrant. Okay, so we will have -π/4 as the inverse sine of -1/2. Okay, so similarly, if you want inverse sine of -3/2, our reference angle there should be π/3. But since we are in the fourth quadrant, we want negative pi over 3. Okay, so yeah, to check our answers, remember that Maple can do some computations for us. So what do you say, Maple? Did we get this right? And yep, 1/6 pi is the same as pi over 6, of course. Okay, so we had cancellation properties for inverse functions in general. So let's see how they look like for our arcsine and sine functions. Okay, so if y is an angle between minus pi over 2 and pi over 2, then the inverse sine of the sine of y takes you back to y. And if x is between minus 1 and 1, then the sine of inverse sine of x takes you back to x. Okay, so for example, if we had inverse sine of the sine of pi over 6. Okay, so sine of pi over 6 is 1/2, and we saw that inverse sine of pi over 6, of 1/2 rather, is pi over 6. So this should take us back to pi over 6. Okay, and if we reverse the order, if we look at sine of the inverse sine of 3/4, okay, doesn't matter that we don't know an angle whose sine is 3/4. Inverse sine of 3/4 corresponds to some angle between 0 and pi over 2, and the sine of that angle should be back to 3/4. Okay, Maple, did we get this right? Equal sign, yep, we're back to 3/4. Now, let me warn you a little bit about this cancellation law. It only works when y is between minus pi over 2 and pi over 2. If we are out of that interval, let's change the pi over 6. Let's make it instead 5 pi over 6. Okay, so I hope you remember. What is the sine of 5 pi over 6? That's just a reflection of pi over 6 across the y-axis. So it will have the same sign as just pi over 6. And that sign would be 1/2. Okay. Oh, but wait a minute. We just saw earlier that the arcsine of 1/2 is pi over 6. So we started out with 5 pi over 6, but we are not ending up at 5 pi over 6. We're ending up at pi over 6 instead. And that's because 5 pi over 6 is out of this interval. Did we do that right? No harm in checking. And yep, we are at pi over 6, not at 5 pi over 6. Okay, we are now ready to do some calculus. What is the derivative of the arcsine function? Okay, so in order to do this, we are going to use what's called implicit differentiation. I hope you remember this from basic calculus. So the setup is, instead of y equals arcsine of x, we will replace this equation with the equivalent equation where x equals the sine of y. Okay, and again, x and y belong to these restricted intervals. Okay, we want, however, dy dx, okay, where y is inverse sine of x. So we will use this equation x equals sine y, and we will do the derivatives implicitly. Okay, so we want the derivative of both sides with respect to x. Oops, let me hide that from you. And okay, there we go, all gone. So we want the derivative of both sides of this equation with respect to x. Okay, so we have derivative on the left of x and the derivative on the right of sine of y. However, whenever we take a derivative with respect to x and our function involves y, remember that we have to use the chain rule. Okay, so the left side is easy. The derivative of x is simply 1. but on the right, the derivative of sine is cosine, so we get cosine of y, but by the chain rule, we have to multiply by dy dx. Okay, so if we want dy dx, we need to isolate it. We have to put cosine y on the left side. Okay, so we are going to get on the left 1 over cosine of y, and on the right we are going to get dy by dx by itself, which is what we want. Okay, so now the problem is, okay, I want 1 over cosine x, but sorry, x is sine of y. So basically we need the cosine of the sine of y. Okay, so that's the part that we need to figure out next. Okay, so we want to get cosine y from x, but x is the sine of y. Well, the idea is to use the Pythagorean identity from trigonometry. Cosine squared y plus sine squared y equals 1. Usually we say that in terms of x, but this time our angle is called y. But since x is sine y, we can rewrite sine squared as x squared. So cosine squared y plus x squared is 1. Solve for cosine squared, we get 1 minus x squared. Okay, but remember now, y is an angle on the right side of the circle between minus pi over 2 and pi over 2. So in that interval, the cosine is positive. Okay, so instead of using plus or minus square root of 1 minus x squared, the cosine of y is simply the square root of 1 minus x squared. Okay, so finally we get to solve the derivative, and we have a corresponding antiderivative formula. The derivative that we are looking for is 1 over cosine, which is 1 over square root of 1 minus x squared. Okay, so cosine is the same as this, so reciprocal. The derivative, in other words, of the arcsine function is 1 over radical 1 minus x squared. Okay, anytime we have a derivative formula, we have a matching antiderivative formula. So the general antiderivative of 1 over square root of 1 minus x squared is the arcsine of x plus a constant c. All right, let's look for a derivative and for a definite integral. Okay, so our function is the inverse sine of 3x. We want the derivative of this function. Okay, so we said that the formula for the derivative of inverse sine is 1 over the square root of 1 minus x squared. So we should have 1 minus something squared. Our something is 3x. Okay, so we want 1 over square root of 1 over 1 minus 3x quantity squared. Okay, but don't forget there's a chain rule involved because we don't have x here, we have 3x. So we have to multiply by the derivative of 3x, which is just 3. Okay, so of course we can simplify this a little bit. We can put 3 in the numerator and we can expand this square. So it looks a little bit better if we write it as 9x squared. Okay, so easy enough. What about this definite integral? Okay, so the corresponding integration formula, I have rewritten it in terms of u, using the letter u instead of the letter x, because, as I mentioned earlier in a previous video, the integral that we're working with often involves a u substitution. Okay, so instead of using the symbol x, we can use the symbol u, which is a little bit more general. Okay, so, whoops, there should be a du over there, my bad. And now that formula is correct. Okay, so the main problem here, though, is that to make this formula work, I need a 1 as the constant inside the square root. Okay, so the problem here is that we don't have 1, we have 25, right? So first thing we're going to have to do is find a way to get rid of that 25. Okay, so scoot this up a little bit. Okay, so what can we do? Well, let's try factoring out that 25 from the denominator. Okay, so we can write it as 25, take it out, factor it out. So the first term now becomes 1. Okay, factoring out is essentially the same thing as dividing out. So we have to divide 25 out of the second term as well. Okay, so we divided 25 from both 25, giving you 1, and minus 9x squared, giving you minus 9x squared, over 25. Okay, so at this point, we can do two things. We can take out the 25 from inside the square root. It becomes 5 once we move it outside. And we can write 9x squared over 25 as the square of something, okay? Because that something is what we are going to use as our substitution u, okay? So we will take the 25 outside. It becomes simply 5. And then we are going to remove that 25 from inside. And now we simply have 1 minus 9x squared over 25. We are now going to rewrite this as the perfect square of something. Okay? So obviously, that something should be 3x over 5. Okay? So there we go. We can, of course, take that 5 all the way out of our definite integral. And now we have integral of 1, square root of 1 minus something squared. So that something is going to be our u substitution. Okay, so yeah, we can go ahead and put the 5 outside. So we have 1/5 of that definite integral. Okay, so we are ready now to make u our 3x minus 5. So du is 3 over 5 dx. Okay, so if you like 3 dx over 5. And once again, solving for dx. So dx will be 5 du over 3. Okay, let's see. We also, shall we change the limits? Okay, so when x is 0, 3 times 0 is still 0. So u equals 0 also. And when x is 4/3, u will be, so 3 times 4/3 divided by 5. So the 3's cancel, and we are left with 4/5. All right, so we are able to rewrite our integral. Okay, so we get the 1/5 stays, and instead of, yeah, let's do this. Instead of 0 to 4/3, 0 is the same, but we now have 4/5. So there's a very subtle change in the upper limit. From 4/3, it's now 4/5. This is our square root of 1 minus u squared. Our dx is 5 du over 3. So let me copy this fraction. And we have 5 over 3 du. Ooh, interesting. Okay. So, yes, interesting because the 5 here is going to cancel with the 5 up there. How convenient. And the 3 here is going to survive. That's going to replace the 5 outside. So let's do some changes here. The 5/3 is gone. 5 cancels with 5. The 3 goes out as 1/3. Okay, so we are now ready to apply this formula. We're integrating from 0 to 4/5. 1 over radical 1 minus u squared du. So this is now simply, all right, this is now simply, we have the 1/3 here, and we need the inverse sine function, inverse sine of u, and we need to evaluate from 0 to 4/5. Okay. So, do we know an angle whose sine is 4/5? No, so we'll just leave it a simply inverse sine of 4/5. But do we know an angle whose sine is 0 and is between minus pi over 2 and pi over 2? That would be 0. Okay, so this is simply now 1/3 inverse sine of 4/5. And shall we put the fraction? Sure. 4/5. And minus 0, that doesn't do anything. Okay, so this is our final answer. Okay, so we're going to go back to GeoGebra now because we're going to construct the arc cosine or the inverse cosine function. I'll see you there in a second. All right, I have erased everything. Start fresh. Now we graph cosine of x. There it is. And just like sine, of course, it is far from being 1 to 1. Okay, so you will hit 2 points there horizontally. I see 4 points of intersection over there. So we have a lot of restrictions to do. So let's start with what we had before, like 1/2 there. So again, we're not going to go far from the origin. But if you go left just a little bit, yeah, you're going to hit 2 points right away. So we have to erase the part where x is less than 0. And we can keep going to the right. Okay, you will still pass the horizontal line test there, except once we go past that minimum there, you're going to hit 2 points. So at minus 1/2, yeah, we have 2 points that we're hitting with that horizontal line. So it looks like we cannot go beyond this minimum. Where is cosine -1? That should be pi. Yeah, about 3.14. So we can't go beyond pi, and we don't want to be to the left of 0. Okay? So our restriction is going to be 0 less than or equal to x less than or equal to pi. And boom, there you go. This function is now 1 to 1. The range is still as big as possible from -1 to +1. Okay, so this time we are restricting between 0 and pi, and GeoGebra can draw the inverse function for us. So arc cos of x, sure. And we get, there you go, that is our inverse function. So it looks very different from what we saw with the inverse sine of function. And that's because the domains are different. For sine and cosine, the domains of restriction are different, okay? But again, we have symmetry. So if you look at y equals x, use that as a mirror, turn your head to the left 45 degrees, then yes, this blue part is perfectly reflected into this red part, and that red part is perfectly reflected to this blue part. Okay, so those are the graphs of the restricted cosine function and the arc cosine function. Okay, so here's what we said in GeoGebra. Our restriction for the cosine function will be actually between 0 and pi, and the y-coordinate will of course be the full range between -1 to 1. Cancellation properties and definitions. Y equals arc cosine of x means that the cosine of y is x, and x is between -1 and 1, y is between 0 and pi. Okay, so before for inverse sine, it was for minus pi over 2 to pi over 2. This is for arc sine. Okay, so take note of the difference. This time, the angle that we are looking for is between 0 and pi. We are now on the upper half of the unit circle in the first and the second quadrant. Our angle is between 0 and pi. Okay, we're looking for an angle whose cosine is within our arc cosine function. Okay, so more trigonometry. Which angle has cosine 1/2? And since it's positive, we must be in the first quadrant, 0 and pi over 2. Okay, so is it pi over 6, pi over 4, pi over 3? I hope you remember that it is pi over 3. Okay. Now, I hope you notice these are the same three numbers that we saw for arcsine. Okay, but of course our answers are different now. Arc cosine of -1 over radical 2. Okay, the cosine is negative. We're in the upper half of the circle. This time we're in quadrant 2. Okay, so which angle in quadrant 2 has cosine -1 over radical 2? I hope you remember that should be 3 pi over 4. Okay, if you're thinking minus pi over 4, you're in the wrong quadrant. And the cosine there is positive, not negative. Okay. Finally, inverse cosine -1 over radical 2. We should again be in the second quadrant. Which angle there has cosine -1 over radical 2? That should be 5 pi over 6. All right, so let's find the derivative of arc cosine. It's going to be very similar to what we did for arc sine. We're going to do it implicitly. So we will let y be arc cosine of x, but that means that the cosine of y is x. X is between -1 and 1. Y is between 0 and pi this time. Okay, so now we start with cosine y is x. We take the derivative of both sides with respect to x. And as before, the derivative of x is simply 1. But the derivative of cosine is now negative sine. Okay, so that becomes negative sine y. Chain rule, we have a dy by dx. Okay, solving for dy by dx, we have 1 over negative sine of y. Before we had cosine of y, now we have negative sine y. Okay, but this time it is our x, which is cosine y. So applying the same Pythagorean identity, cosine squared y plus sine squared y equals 1, we now get x squared plus sine squared y equals 1. So solving for sine squared, we get 1 minus x squared. This should look familiar, okay? Before this was our cosine squared of y. This time we have sine squared of y. It's 1 minus x squared. Okay, so before I scroll down, our y is between 0 and pi, okay, upper half of the unit circle, okay? We're looking for the sine of that angle. Sine is the y-coordinate, okay? So the sine of an angle between 0 and pi is going to be positive, all right? So instead of plus or minus, we only get plus square root, okay? So that means that the derivative of inverse cosine is 1 over minus sine y, which is 1 over square root of 1 minus x squared. That is the same as the derivative not of inverse sine of x, but the negative of inverse sine of x. Okay, so we saw this in basic calculus. Two functions can have the same derivative, but only if they are different by a constant. Okay, x squared, the derivative is 2x. X squared plus 5, the derivative is also 2x. 5x squared, the derivative is 10x, not 2x. Okay, so you can add a constant to a function and not change its derivative. And according to the mean value theorem for derivatives, that's the only way two functions can have the same derivatives. They must differ only by a constant. So it means that arc cosine of x and negative arc sine of x must be different only by a constant, by a plus c. Okay? If we scoot this over to the left, it means that arc cosine x plus arc sine x must equal a constant. Okay? How do we find this constant? Plug in a number, like 0, exclamation point. So we get arc cosine 0 plus arc sine of 0 must be that constant. So 10 minutes ago, we said that arc sine of 0 is just 0. But what about arc cosine 0? What angle between 0 and pi has cosine 0? Cosine is the x-coordinate. I hope you realize that that is pi over 2. All right, so pi over 2 plus 0 must be our constant. So our c must be pi over 2. Okay, so there we go. We have a beautiful relationship between inverse cosine and inverse sine. Their sum must be pi over 2. Okay? So, unfortunately at this point, it means that inverse cosine of x is a redundant function. Okay? Anything that we can do with inverse sine of x, we can do with inverse cosine of x. Okay? We only need one of them. We will decide to keep inverse sine of x. All right, last but not least, we are going to construct the inverse tangent function or the arctangent function. So I'll see you in GeoGebra in 1 second. Okay, so we want tangent of x, and woo, there we go. Again, periodic, but this time, I hope you remember, the period of the tangent function is not 2 pi, it is only pi. Okay, there's pi over 2. We have a vertical asymptote here, and negative pi over 2, another vertical asymptote. So here is one complete period. And again, if you draw a horizontal line, right now we're hitting it at 3 points. Okay, so obviously we have to restrict our function to at most 1 period. But when we did that to sine or cosine, that was not enough because there were still repetitions between 0 and 2 pi. But now we have a smaller domain, and it looks like it is strictly increasing between minus pi over 2 and pi over 2. Is that really true? Well, what is the derivative of tangent x? I hope you remember, it is secant squared of x. Square a number, it's always going to be positive or 0. Wait, can secant be 0? No, it's the reciprocal of something, of cosine, so it can never be 0. So the derivative is strictly positive, which means that your function is strictly increasing within one domain. Okay, so we will restrict our tangent function to be between negative pi over 2 and positive pi over 2. Boom. Okay, so therefore it is now a one-to-one function. And because we have vertical asymptotes at pi over 2 and minus pi over 2, our range is no longer minus 1 to 1. Far from it, it is now all real numbers. You can go all the way down to minus infinity here and all the way up to positive infinity here. Okay, so, we tricked GeoGebra a little bit. We're not supposed to plug in pi over 2. So strictly speaking, that should be less than. Okay, so now it got mad at us. So we will graph tangent x, 0 less than x less than, minus pi over 2 less than x less than pi over 2. Okay, so there we go. So GeoGebra doesn't seem to mind that you plug in a number which it should not compute. It's not going to complain too much. Okay, and now we can graph the inverse function. So this time, okay, so let's think about this. The domain of tangent restricted will be between minus pi over 2 and positive pi over 2. The range is all real numbers. So for the arctangent function, the domain will be all real numbers, and the range is going to be from minus pi over 2 to positive pi over 2. Okay, but we have a little bonus here. We have vertical asymptotes at pi over 2 and negative pi over 2. Okay, so again, the graph is going to be flipped over, reflected across y equals x. Let's draw the mirror. Okay, so we can almost imagine it, okay, before we actually graph it. So that will flip across y equals x. The vertical asymptotes will turn into horizontal asymptotes. So let's see. arctangent of x. Boom, there it is. Beautiful. So instead of vertical asymptotes, we have horizontal asymptotes. Let's draw them. Y equals pi over 2. There it is. And y equals negative pi over 2. Okay, there it is. Okay, so we can also write this out as a limit. Okay, the limit of the arctangent function as x goes to infinity is positive pi over 2. The limit as x goes to negative infinity is negative pi over 2. Okay, so let's summarize here what we did for the tangent function. We restricted it from minus pi over 2 to pi over 2. So in that restricted domain, the range is still all real numbers. But we should not include the endpoints because we get vertical asymptotes at those points. So this time, instead of closed minus pi over 2 to closed pi over 2, we now have an open interval. Y equals arctangent of x means that the tangent of y must be x. X is any real number, but y must be an angle between minus pi over 2 and positive pi over 2. Okay, so the similarity is between inverse sine and inverse tangent. They both have the same range, except that we don't include pi over 2 and minus pi over 2 for arctangent. Okay, so this time we need different numbers to play with. We can't use 1/2 and radical 3 over 2 anymore, blah, 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 because the tangent of our famous angles are now either, well, you tell me. Do we know an angle between minus pi over 2 and pi over 2 whose tangent is 1? Okay, do we remember? That angle is pi over 4. Okay. So if that's pi over 4, then the ones involving radical 3 is either one or the other, pi over 6 or pi over 3. Okay, and we have a negative tangent here and a positive tangent here. Let's do the positive first. Okay, so we're in quadrant 1. Who is the angle in quadrant 1 whose tangent is radical 3? Okay, so the other choice is 1 over radical 3. Radical 3 is bigger, so that must be the angle pi over 3. So it's pi over 3. Okay, so that must mean that this arctangent must be the other angle, pi over 6, but we are in the 4th quadrant, so it must be negative pi over 6. Okay, now for the calculus, we want the derivative of the arctangent function. Same strategy, we'll do it implicitly. So if y is the arctangent of x, that means that the tangent of y must be x, where x is any real number, and y is between minus pi over 2 and pi over 2. Okay, so we will take this setup, tangent of y equals x, take the derivative of both sides with respect to x like before. Derivative of x is just 1, but the derivative of tangent, we mentioned it in GeoGebra, it's secant squared, but instead of secant squared x, it must be secant squared y. Our variable is y, but by the chain rule, we need dy by dx. So this time dy by dx is 1 over secant squared y, and you might be tempted to say, oh, wait a minute, that looks familiar. 1 over secant is just cosine. Okay, because secant is the reciprocal of cosine. Okay, however, we are going to stop you a little bit because we're not done. Okay, remember before we had to solve for cosine y or negative sine y, whatnot. This time we need to solve for secant squared y. Okay, but it came from x over here where x is tangent y. All right. So we had the basic Pythagorean identity, cosine squared y plus sine squared y is 1, but we want the one which involves secant squared y and tangent squared y. So I hope you remember, all you have to do is divide both sides of that equation by cosine squared y, so that cancels and becomes 1. Sine y over cosine y, that's your tangent y squared. 1 over cosine squared y is secant squared y. Okay, so that's the identity that we want. So our derivative is 1 over secant squared y, which is 1 over 1 plus tangent squared y. So that becomes 1 over 1 plus x squared, because our tangent y is our x. Okay? So therefore, the derivative of the arctangent function is 1 over 1 plus x squared. Okay? It looks similar to the derivative of the inverse sine function, where we had square root of 1 minus x squared. Okay? So careful, there is no square root in this formula. Okay? But every derivative formula has corresponding antiderivative formula, so we can rewrite this as the antiderivative of 1 over 1 plus u squared du is inverse tangent of u plus c. So let's do an integral. All right, our last example. We want to find the antiderivative of 1 over 9 plus 4x squared dx. Okay, so this is a little bit similar to what we had for arcsine, where I had 25 minus something squared, and we did a definite integral in that problem. Okay, so remember that one of the issues, the first issue we had to resolve was there was a 25 there. Okay, so now it's a 9 instead of a 1, but it's really the same idea. Okay, we simply factor it out or divide it out. Okay, but there is no square root this time. Okay, so we are dividing by 9. There's nothing that we have to take out. Okay, there is no square root, so it simply factors out as 9, divides out by 9. Okay, and well, if you like, you can take it out of the integral. So it will be 1 over 9. And then, whoops, don't divide by 0. Inside the integral, we will have this. We don't need the parenthesis anymore. We can rewrite that as something squared. Okay? So if you want something squared, that should be 2x over 3. Okay, there you go. So now we have 1 over 1 plus u squared. Okay? So we have an obvious u substitution. U will be 2x over 3. So du is 2 dx over 3, and dx is 3 du over 2. Okay, so we are ready to do the substitution. Okay, so what we are looking for is 1/9, and our denominator is 1 plus u squared. Our dx is 3 du over 2. Okay, so let me insert a 3 over 2 du. Okay, very good. If you recall, for inverse sine, we had a 5 here and a 5 there. No, wait a minute. No, it was the, yeah, it was a 3 if I'm not mistaken. And something survived. Okay, something else survived. Okay, so this time, the 3 and the 9 don't cancel each other out completely. Okay, so a 3 survives outside, and you have a 1/2 over there. Okay, but you can take that 1/2 outside, and you will simply get 1/6. Okay, so something different happens here because we don't have that square root. Okay, there's a big difference. Okay, we are now ready to apply our formula. It's simply inverse tangent of u. So I'll just copy that over and bring back u. U is 2x over 3. I should say bring back x, right? So that will be inverse tangent of 2x over 3. There you go, just enough room. Okay, that's our video for today. Much longer than our first video, but still under 1 hour. So I consider that a win. Thank you so much for watching, and I will see you next time. I hope you enjoy the rest of your day. Bye.